begin, I want to quickly talk about how do chemical reactions occur. There are three fundamental criteria. One, there needs to be sufficient energy to overcome the activation energy. As you can see this diagram here, we've talked about it before. We'll talk about it a little bit more in a second. Particles need to collide. So the idea is, in order for a chemical reaction to occur, things need to smash into each other, need to collide into each other. The other part is, when they do collide, they must be orientated in the right position. So they can collide, but if they're not in the correct position, you won't get a reaction, or when they collide, they must have enough energy to overcome the activation energy. If they can't do that, then it's not a successful chemical reaction. Okay. So looking at examples of having good collisions, one is by having enough energy. You can do that by simply increasing the heat energy in a reaction vessel. So maybe if you have two mixtures in a beaker, if you heat it up with a Bunsen burner, you can increase the energy in those particles to make it collide a bit more. That can either form or break chemical bonds. The other example I did talk about was just having the right orientation. So you can see in this position here, we have our chemical, and our chemical here. So the engagement with the chemical is one of the oxygens is going to be collided with the carbon, and as you can see, that gives us carbon dioxide, CO2, and we have NO2 here. Say for example we have this diagram here, and we don't have the correct collision, or this one here. You can see we have an oxygen colliding into an oxygen, and that won't give us the molecule we want, right? If we have the carbon facing the oxygen, then we can get CO2 forming. So orientation is important, as well as having the right energy in that collision point. Now, as a consequence of having sufficient energy, you might get a reaction that is exothermic, which is releasing heat, or you might get one that is endothermic, where heat is absorbed. Say for example with activation energy, which helps us determine whether or not something is exothermic or endothermic. It's an energy barrier. So it's how much energy something needs in order to perform a chemical reaction. For an endothermic reaction, you can see it takes a lot more energy than it does for an exothermic reaction. We measure this based on the peak of what we call the transition state. So the point at which particles begin to transform, or elements begin to transform into a different substance. And then we have the bottom peak of the energy of the reactant. So it's determined by these two marks here. We can see that in an endothermic reaction, the products will have more energy than the reactants. Hence, that's because of energy being absorbed in the reaction. That's why the surrounding gets colder. If we're looking at exothermic reaction, the reason why the surroundings get warmer is because the products have less energy than the reactants, hence it releases energy to the surroundings. Another way of thinking about it, if you have bonds being broken, energy must be absorbed to break the bond. Imagine you have a piece of branch, you need to apply energy to break the branch apart. And then energy is released if you form a new bond. Okay. So just keep that in mind. That's what we refer to in endothermic. Energy is absorbed to break bonds. Something is exothermic because energy is released, as you can see here, to make new chemical bonds. That's the difference between the two. So let's look at decomposition reactions again, using the lens of now knowing it's exothermic and the difference of endothermic. So decomposition reactions are endothermic because, as you can see, we're breaking the bond apart. This is where we have a single compound breaking into two or more. So remember, the key word here is it's that actually affect our daily lives as well. Think about a soft drink. Okay, you drink Coca-Cola, you drink Pepsi, Fanta and all that. When you first open it, you hear that kind of fizzling sound of the bubbles coming through. That's actually a decomposition reaction you're witnessing there. So when you open the can, it causes this chemical reaction where we have a thing called carbonic acid, which is H2CO3. It decomposes into carbon dioxide and also water. So that fizzing you're tasting is the carbon dioxide that is being dissolved back out in the solution, like the bubbles we see here. What we also know is this reaction gets faster when we increase the amount of heat, which is why if you leave your soft drink during warm weather, you tend to find that the fizziness or the sting, the acidity to it, is lost after a period of time. And that's because of the speeding up of decomposition. Another example, if you're a baker or if you like cooking, is through baking. So using sodium bicarbonate, aka baking soda, it will decompose into sodium carbonate, water, and carbon dioxide. It's this carbon dioxide that gives the rise to bread when the yeast is eating through the glucose in your bread. So that's where it is. It also gives it really nice texture with the little air pockets in the bread. So that's another example. Our example number 3 is the airbag inflation. So we have a thing called sodium iodide, which rapidly heats up upon collision. Now, just for your own information, for an airbag to be ignited, it's about 20 kilometers to 25 kilometers per hour you need to be traveling in that collision. When that breaks apart, it forms sodium, which is a highly reactive metal, and nitrogen. So that's the thing that cushions you, that's the thing that protects you when you go through a car crash. As a matter of fact, 80% of the Earth's atmosphere is made out of this stuff here. We have another one, which is this one here. Don't know if many of you use these or know of this, but if you're wearing glasses and it turns darker when you expose it to the sun. Now this is a really special type of decomposition reaction. It's called photolysis. So it's a chemical known as silver chloride. This breaks down into silver and chlorine only when exposed to light. So that's why when you're not outside exposed to UV radiation, and I do want to highlight, this is when we say light, we actually mean by like UV radiation here. So I'll just quickly fix that. Okay. And so that causes the darkening. Now, the darkening process is caused by the production of silver. So that's where the darkened color comes from. This actually is a reversible reaction, so you don't just get random sunglasses and you can't use them as reading again. If you take away the light, that actually encourages the reaction to go back in this direction. This is known as a equilibrium reaction or reversible reaction. A bit more on that in year 11 and year 12 if you're interested. Okay, let's go to some questions about decomposition. So firstly, what's the difference between a decomposition reaction and a combination reaction? Well, a combination reaction is firstly also known as a synthesis reaction. So decomposition, we have a single compound breaking into smaller components. With a combination reaction, you have two or more smaller, it could be elements or compounds, combining to form one larger substance. Or compound or molecule, whichever word you like. Compound is probably the more correct term to use in this case. There's that. Question 2, it says identify which of the following is a decomposition reaction. So as you can see here, we have water. It's broken apart into two components, single compound breaking into smaller components. So this is decomposition, call it decomp. This is not a decomposition reaction. We have two smaller components forming one larger one. So this is actually a synthesis reaction. This one is not an example of decomposition. If you actually have a look, it's known as a single displacement. The reason being is, firstly, there are two compounds, or one element, one compound, and they form something else. Decomposition is one reactant breaking into multiple components, so that's not correct. And this one as well is not a decomposition reaction. It is also, well, this one is actually a combustion reaction, which is also a single displacement reaction. So there you go. Last one is to write a balance equation for the thermodecomposition of calcium carbonate to form calcium oxide and carbon dioxide. Now let's think about it this way. Calcium carbonate, calcium is Ca, carbonate is CO3, calcium is 2+, carbonate is 2-. So we don't have to do anything with valencies. This is what we get. They decompose into calcium oxide. Calcium oxide is CO, so CO. Again, calcium here is 2+, oxygen is 2-, so we don't have to do anything here. And carbon dioxide, CO2. So there we go, straightforward enough. You can also see that in most cases, whatever decomposition component you're looking into, you can just read off the wording. So we have silver and bromide. So silver is +1, bromide is -1, so it's AgBr, just as it is. No, even with crisscross, it's just 1 and 1, so nothing to do. And then we get silver, and we also have bromine gas. Now bromine gas is a 2, because it is what we call a diatomic molecule, so it comes in pairs, or anything that says gas comes in pairs. And so to balance this equation, we need 2 bromines on this side, so we write a 2, which means that I have a total of 2 silvers and 2 bromines, which means, given the fact that I only have 1 silver here, but I have 2 bromines here, I need an additional molecule or element here. So there's that. That's how you do the questions. Now there's a little bit more for you to look into, so check the link. But this gives you a nice little summary of some examples of decomposition reactions and working out, writing chemical equations, and also we can even write word equations of demonstrating the type of decomposition reactions we see. Alright, so thank you for listening up till now. My name is Mr. Wong. Hopefully you enjoyed this lesson of chemistry, and I will see you